proof assistant, but we've taken a bit of diversion into category theory to try and understand co-induction. But it's very difficult for me anyway.
That's fantastic. I have been looking on and off into Cork and Isabel and Lean and just trying to figure out, what is really worth pursuing because they all seem to have their pros and cons.
Exactly.
So that's really fantastic that you actually have been studying it.
Yeah. But I'm really intrigued to see how this study group works. I have to say that I've had Knuth's books for a long time, and I tried to read them, and it was very, very tough. Yeah. So I'm very intrigued to see how you read it and what, how do you write programs, and it's all fascinating to me. So we'll see. We'll see how it works.
That's great. Well, it's been a journey and it's continuing. So, we welcome you. And we also welcome Srivatsa. Is that right? Am I pronouncing it right?
Yeah. Hi.
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 Welcome.
Thanks. This is my first time. I just noticed a link to this somewhere yesterday. I think somebody had written a blog post about something, and I'm intrigued as well. So I'm just joining.
Great to hear that. Great to have you. Yeah. So we do have at least 3 regulars, sometimes 4, and then people have been joining on and off. So we'll see how it goes today. I did see one prompt just a second ago, but it disappeared quickly. So I'm not sure if they disconnected or I did something wrong. But generally we wait till about 10 past the hour, and then we'll get going. So go ahead.
So you're in New York, and sorry, I can't see your name now. Whoops, it's disappeared.
Okay, so let me just introduce myself.
Yeah.
I am Zartaj Majid, and I am in New York City. And you'll see 2 tiles for me. I'm using one to present the slide and then one for myself with the camera. Hi, Michael, Miguel. So we have 2 new members today. I think Miguel is having some connectivity problems, but hopefully he'll sort it out. If you don't mind telling us where you're connecting from, Paul and Srivatsa.
So I'll go first. So I'm in London. I'm a software engineer. Got a bit of a academic maths background, and I find art of computer programming very intimidating, but I'm also very interested in it. So I'm really happy to find this group.
Hi, I live in Sunnyvale, California, and I'm also a software engineer. I've been in, I guess I attended one of Knuth's public lectures, and I think I've been interested in his work since. But I have read a few pages here and there, but never systematically more, probably not, never more than 1 page at a stretch. So I'm interested in doing something reading as well.
That's great to hear. How long ago did you attend one of his lectures?
I think I first moved here in I don't remember now, 2014 I think, and I attended everyone since then. So I attended 4 or 5 of them.
Oh wow, fantastic! Is that are you referring to his Christmas lectures?
Right. That is
that's really wonderful. I look for you in the audience because I know they have a lot of the YouTube videos up for those lectures. So, and I've gone through a couple of them, but yeah, fascinating.
Yeah, it's
very nice. And so these are our 3 regular members who've been very diligent in sort of moving us regularly through the text. So there's Michael, Miguel, and Arthur. If you just want to introduce yourselves, please feel free to do so.
All right, I'm Arthur. Hello. And yeah, I've been here since the beginning. Somehow I found this on Meetup. Seemed neat. In real life, I'm a C++ programmer and a corporate trainer. So if you know anyone who needs C++ instruction, send them my way. I'm easy to find. I have a blog, etc., etc. Yeah. And Zartaj is really the one running this whole thing. He says we're keeping it alive, but he's the one coming up with the curriculum and all of this. So, you know, well done.
I'm Mike Zalewski. I'm from New Jersey. I'm a software engineer as well. I'm working at for a healthcare insurance company. With all the changes that have happened in the last year, I've been pretty busy.
I don't think that's going to let up, Michael. I think, if anything, that's going to get even more intense, right?
Yeah, well, I started, I don't know how much you guys know about healthcare, but I started, the coding system for healthcare claims was changing from something they call ICD-10. And ICD-10 are the procedure codes that they put on the form, and all of those codes changed. And there were, I called it the Healthcare Software Engineers Full-Time Employment Act, because there was ICD-10, there was healthcare reform, and there was what do you call it? The markets, that come with healthcare reform. Healthcare reform had a lot of mandates that they had to follow, and then there was the whole new market for the what is it? Where people without insurance can go. The name is escaping me right now.
Is it basically the ACA?
Healthcare exchanges. So that was a whole new channel by which business was coming into these insurance companies. If you wanted to participate in the exchanges, you had to allow people to enroll over the web through the government, which was a whole different way of doing business, really. So anyway.
Well, I'm Miguel, software developer in New York. I do a lot of Scala, so very high level all the time. I was very surprised when we started this, and then I stumbled with we have to do assembly and stuff like that. It was very surprised and pleasantly surprised, because that's something that I have never had to do in my life. Like thinking these low level terms, but at the same time abstractly, right? In the abstract way, thinking low level. Like we're talking about algorithms. So how can you actually implement them in the actual computer without the runtime holding your hand? Like you are actually do the real deal, So that still is intimidating after I don't know how many sessions. But this is, I can see how it is opening my head to, my mind. When I think in my daily job, I don't have to use any of these things. But when I think, wait a minute, I recognize this pattern, and I know I cannot actually visualize the whole implementation because that's impossible. But I gain some intuition about how this must. There is no magic bullets, like when you're doing stuff in computers, maybe you guys happens to you, that things just everything works. You just have to worry about what I'm doing. That's not true. Like everything is being built from very simple pieces, and this book, at least to me, is really helping me to visualizing those small pieces that are my computer, where I work. So welcome.
Wow, that's great, Miguel and Michael. Yeah, so let's get going. This is our agenda for today. And just to provide some background on where we are, we did start out with the first volume. So as you know, there are 4 volumes so far that have been published as books. And then there is a 5th collection that's also called Volume 4, but Volume 4B, that's supposed to be published next year as a book, although its pieces have come out already. So there's a lot of material, and you probably already know this. We started out with Volume 1 with some very basic data structures. And then we quickly moved to Volume 3, which are more sort of application-oriented material. And we started with the sorting chapter. And we spent some time in there. I would say that we covered maybe 70 to 80% of the sorting content. And then we came back to Volume 1, which is where we are now, because the more advanced material was dependent on trees and some other more advanced data structures. So now we've been covering trees for the last 4 or 5 meetups. And I would say that, again, we're about 3/4 to 80% of the way through trees. If you have a background in programming and computer science, which it sounds like you do, none of this will feel very strange. So if you want to just progress with us from this point on, I think you should be fine. But if you do want to review the previous material, we do have our meetups all recorded. There's some supplementary material in terms of programs and explanations and notes, and all our chat comments are posted on our GitHub repo. So there is that available. Personally, I feel that it's very worthwhile. Even if you think that you recognize the topics and you know these algorithms or even have used or implemented them, Knuth has a very distinct way of presenting algorithms, and a lot of his, I would say, his tweaks and versions and variants are very special and really worth understanding. So having said that, today we are looking at trees. We started out with binary trees, spent a bit of time on that, and then we looked at how trees could be represented in memory, depending on the kinds of trade-offs you want to make in terms of, let's say, space optimization versus some algorithmic convenience. And today we'll just continue with that. The focus of the initial portion of the reading is going to be this algorithm to do polynomial arithmetic. And we'll see a representation using trees that can help us do that. That'll be followed by a section that is a little more theoretical, which is going to be a little new for us, because while we have looked at some of the theoretical parts of the text, we've generally avoided them because they require a lot more concentration, a lot more time. The hope is that people who are really interested will be able to do so in their own time and maybe tell us about it. But there are a few sections, especially with trees, as you may well know, that establish certain properties for trees that are very useful algorithmically as well. So I do feel like these will be really worthwhile. And so we'll start with this section on path lengths. And it does lead to an algorithm. So there is some practical benefit that we will also study. So the process, I remember Paul asked how our meetup is structured and how we go through the text. So the idea is that we read together for a little bit, generally 5 to 7 minutes, and that's usually not more than a couple of pages. And once we're comfortable with what we've read in that allocated time, then we discuss that material. There's generally no time limit on the discussion, but we do want to keep it reasonable and make progress. I'll put up a slide saying exactly where we are, and I'll try to provide some text snippets that'll help you bound the part of the text that we're reading. As we read, highly encouraged to put in any thoughts and comments that you have, questions that you have in the chat. If you want to speak up, that's fine too, but we do have that discussion period where we discuss things aloud and we go over any questions and clarifications. And usually I'll ask somebody to summarize some of the material, and there's no pressure, there's no stress. So whatever you understand, even if it's just questions, that's great. So please, I would encourage anyone to volunteer to voice out what their response and their reaction has been to the reading. And then everything is recorded and posted to YouTube, posted to GitHub. I am falling behind as time goes on, so I haven't posted the last 4 or 5 meetups to YouTube, but hopefully this long weekend will allow me to catch up a little bit. And sometimes we feel motivated enough to actually implement the algorithms. Arthur has done quite a bit. I've written quite a bit. And so all of this material is available and, obviously available for anyone who's not even in the meetup. So this is where we are. I do want to point out that we at least the slides will refer to the latest editions of the text. So I do know that people have older editions, so you may need to reconcile some of the page numberings and the snippets. But you can always ask us, and we'll guide you through the part that we are actually on. So chapter 2, and this is 2.3.3. Other representation of trees, pages 355 to 357. And I've got these 2 text snippets. So this, sorry. I guess I cannot click on the slides when it's being presented. So, but the bottom 2 lines, the first line represents the start of the reading, the second line represents the end of the reading. And we have about 7 minutes till 2:26 New York time. Okay. So did anyone figure out the diagram D on figure 28, how that works?
Yes, but it's crazy confusing.
So how does it work?
So remind me something, the right link always points to your first children, right? In this case, or this is entirely different?
I think this is, I mean, I've been thinking of this as entirely different from the tree.
I mean, it would be very weird because all trees before this one and all trees after this one are always binary trees with this weird form that the right link always points to the children and the left link always points, no, the other way around. The left link points to your siblings, the right.
Yeah, so I think, Miguel, you're trying to describe the binary tree that corresponds to a generic tree. Where
right. So my question is that what he's doing here, or is it entirely just a regular tree?
No,
with a bunch of links?
This is definitely not that. He's calling these left and right, not L link and R link.
Right.
Specifically.
Fair enough. Yeah, you're right. Yeah.
Link and R link. In a binary tree, you have L link pointing one place and R link pointing at, like, you know, down to one child, down to the other child. But here, left and right are opposites. Like if you're on my left, then I'm on your right. The left and right arrows are just, it's just a doubly linked circular list. Or this is a collection of circular linked lists.
Yeah, right. Yeah.
Linked together with their up and down fields.
Okay, maybe we should just step through the lettered parts like A, B, C, and D of figure 28. So if we look at, so the fields obviously in figure A or 28A, that is just the layout. But then how is a constant, which is a polynomial, what is that representation in 28B?
Is basically saying here if you're saying this is the sort of root of the polynomial, this is the top level of it, then you don't care about any of those other grayed out fields, and you're just saying its constant value CV field is some integer, and that's going to be its value, and its down pointer is null, meaning it's just that value, not that value times anything.
Is CV coefficient value? Is that what it's supposed to be?
Or constant, or yeah.
Or okay. And then 28C. Now we have a polynomial in
maybe CV.
one variable.
So a polynomial, well, this is not necessarily a polynomial in one variable, but it's a polynomial in at least one variable. It's a polynomial that definitely has some terms involving x, and
yeah.
They may involve other terms, depending on what G0, G1, and Gn end up being.
Sure.
I just forgot, this says CV might stand for constant or variable name. And yeah, that actually sounds really good to me.
Okay. Okay, so then why is x at that root?
That's the name of a variable.
Okay.
That's the V, I guess.
Yeah, it means what it says on the top there, that it's as a function of x, you have G0 plus E1 times G1 to the, well, yeah. No, it would be
X raised to the E1 times
G1 times X to the E1 plus Gn times X to the En. So that's how variable X is decomposed. If you look at that polynomial at the top, the G1 and G2 can be functions of Y and Z.
Okay.
So if you look, they're not constants. And if the G0 is Y, let's say, then that first node that's shaded out, it's going to have a Y in there. And then what's below it is going to be how the function of Y breaks out.
Although completely.
So each GI could have a tree hanging off it? Sorry.
If it's a variable, yeah.
Mm-hmm.
If it's a constant, I think that would be the end of the list.
Yes, but if it's like you say, if the GI could be a whole another polynomial expression, so you could have
exactly. Then the
a
whole
tree hanging off it.
Is going to be down on the next level.
Right.
Yeah. So that's where the recursion is coming in.
Right. So if you look at D, look at D, the middle node on the very left is some function of x. What function that is? It's 3x plus x squared. And I guess it's 3. No, that's a 0. So it's the 3 plus x squared. That's the first part of the polynomial.
Except it's not actually the first. Or wait, now I'm confused. Yes, it is the first.
Can we
part.
go back to the previous one? Michael, in 28C. Michael, in 28C, where we have the G0s and the G1 and G2, what are the left and the right? What's the meaning? What's the semantics of those links?
The left and the right? Okay, so if you have a polynomial of a bunch of variables, the thing that goes in the top is any one of those variables, so x, okay? And then what comes on the next level is a linked list. Don't think of it as a tree. Just think of it as a linked list, and it's a doubly linked list.
Okay.
He made it that way. Mm-hmm. It's a doubly linked list of everything. I don't know how to explain it.
Terms. Each of the terms in X.
Each of the terms in X, right?
Yep.
So. Yeah, so it could be a whole polynomial, in which case there's going to be more levels below it, but and then each node is a different exponent in X. So the first node is X to the 0th, so that would really be that leftmost node is really terms that don't involve X at all, because X to the 0th is 1.
Does this imply that the linked list portion is ordered by the degree of that variable?
Degree meaning the exponent.
Yeah, degree meaning the exponent.
I don't see any reason why it has to be, but it certainly is in the diagram below.
Yeah. Okay, so that horizontal level are the terms in that variable. Each of those terms point up to the variable that they are supposed to be representing.
Yes, exactly.
Okay.
Exactly. So the middle node on the second row is y to the first, and it's or y times some variable to the first power, and to get that variable you go up. So that represents the term yz, and of course we don't know what else is on that term. In that term, it's going to be an x that you're going to find below, and probably something else too. YZ. No, that would be.
Well, it's not yz to the first. It's some polynomial of y.
Exactly.
That polynomial isn't just y. It's actually 0 y's, right? Or it's xy.
Yeah, 0 plus.
No, it's not even xy. Jesus. It's xy. xy times z to the first.
Exactly.
Okay, so now we're looking at 28D, and why or how do we come up with which variable is going to be used as that sort of representative variable?
At the top, you mean?
Yeah, at the top, right.
You could come up with you could pick any one.
Well, Knuth specifically picked the great. He starts with z and goes backward from z, so that there is a unique representation, right? Because we're sorting the variables as we go down from like z, x, y, and we're sorting the exponents from 0 counting up. So I think for any given polynomial, there is exactly one tree that represents it, following all of Knuth's rules.
Not even sure of that, because if you put z at the top, he's got in the middle node, he chose y for some reason. And in the first and the last node, he chose x. That middle node, you could have put an x in there. and then the
You've chosen an ordering of the variables.
It does
So,
seem like he has
it
chosen an
depends on an
ordering of the
ordering.
variables.
What kind of ordering of the variables?
So
I'm saying that
lexicographic
middle
ordering,
node- that middle
lexicographic ordering, or reverse lexicographical ordering of the variables.
So again, Michael, I think so you're looking at that middle row and seeing x, y, x and saying that seems arbitrary. But remember, across the row, in all of the siblings, all the sibling children of that root node, what we're actually sorting by there is the exponent. So we do exponent 0 in the left child, and then exponent 1 and 3.
Right. Why couldn't you put an x there?
In the middle child, why couldn't we put an x? Because we have to work in the y somewhere, and we couldn't put the y below the x because y is lexicographically greater than x, right? That middle tree, that W-shaped tree in the middle there, has to involve both y and x, and we have to introduce them in that order, backwards lexicographic order, because that's the convention we chose. It's the same reason that we started with z.
Okay. Then that leaves. But I think it would work. I think if you didn't have that rule, you could put an x and then figure out what the nodes below wouldn't look the same. But
yeah.
I agree.
So it depends on an ordering. So this diagram depends on the choice of ordering.
So as you go down, the first thing that as you go down any path, pick any of the several paths that go down to the bottom. You're going to hit z first, then y, then x, or you're going to skip. Like z to x, and if you go from z to x, you're never going to have a y in a lower level. Okay.
Yeah, and I think that this gives us, given that convention, I think this gives us exactly one tree representing a polynomial. So if we want to argue the same polynomials, we can just linear
that, and also as you go from left to right, the exponents have to increase.
Yes.
If you do that, then it seems clear to me that there would only be one representation.
Okay, good.
Good. Everyone feel like they have a pretty good handle?
That I'm happy?
Yes. If you're happy, we're happier. Definitely.
Okay.
So just to, again, provide some background, early on in I think chapter 1, there is a section on circular lists. And this was one of the very first applications that we saw of data structures. And it was the same problem, addition of polynomials and multiplication of polynomials. And in those circular lists, they kind of resemble these middle horizontal layers. Except they weren't doubly linked. They were just circular, right? So the tail did point back to the head, but in between you only had one direction. The simplification that was made there was the assumption that each polynomial would have 3 variables. And so that allowed Knuth to divide one of the fields of the structure into 3 portions. So let's say you have, an octabyte, which is what he calls 8 bytes. So you can, have roughly like 2 to 3 bytes per variable, and those were used for the exponents of those variables. But that's what he's referring to when he said that was a little restrictive, and so this is a more general representation and should work for a polynomial in any number of variables. But yeah, it does get complicated. Okay, so let us now look at how this will be used for addition of polynomials, and we'll just continue where we left off, pages 357 to 359. This is essentially the algorithm A. It is a little long, so to be fair, you would probably need a bit more than 7 minutes to really digest this. But if you spend more than 7 minutes, I feel like you could spend an hour on this. So it's not really going to buy you much. And then hopefully the discussion will allow us to hash things out. I should also point out for our new members that we are reading the text together with an updated version of the computer that Knut designed, and Arthur is holding that text up. It's available online on O'Reilly and, of course, in paper as well. And so a lot of the content that is specific to the architecture, so for example, obviously the code in assembly, but also sometimes data structure layouts in memory, they will have their equivalents in the MMIX supplement. So as is the case here, today it's not really that important. So if you don't have it, it's fine. If you have it, just glance at it and you can see what the differences are. So we will read till about 2:50 and then discuss. Okay, who wants to take a stab at explaining any one or two of the steps? You don't have to go through the entire algorithm, just anything, whether it's just the finding the right terms to add, or insertion or deletion, whatever it is that you got out of it.
Well, the interesting part to me about echoing, the interesting part about the algorithm is that it doesn't really need to traverse all of Q, just all of P. And in general, it works by going down on P until it finds the bottom, and it does what it needs to do, either insert that P into the polynomial for Q, or adding the two together. And then it really goes from right to left. It says follow the left, but that's really going to go wrap around to the right and go all the way back to the left, recursively repeating the same thing. And then there's some interesting things that happen, like if you add two terms and you get a 0, then that will cause a whole row of Q to be deleted. Because now you're multiplying that whatever it is by 0 because of cancellation. So that's a high level of what's happening.
Can we try adding at least a few terms of the examples that he provides? So one is obviously the polynomial in 28b, and then the second polynomial he's given in the paragraph after the algorithm. So I'll paste them here in the chat, and let's see if we can work something out.
Well, you need to break that second one down into a representation.
Yeah, strictly speaking, yes, but maybe we can just try one term first.
No, I mean, I think the first step is, as Michael says, like you need the tree form before you even know what the first step is. Yeah. So we should be able to come up with that.
Yeah, it's just X, Y, and Z, so it's gonna be the X, Y, and Z term. So it's gonna be the X, Y, and Z with a 1, exponent of 1. There's no constant terms in that other polynomial, so that's a little interesting.
So I'm thinking that the first step is rewriting the polynomial. Yes, you're okay. You've written that second. So that's the first step in factoring this polynomial down. Right? We say we have z to the 0 times this polynomial plus z to the first times this polynomial plus z to the third times this polynomial.
Sign for the middle term, like z to the 1 times minus x.
Oh, yep, you're right. And am I doing the right polynomial? What was the original polynomial? Am I just doing the example one? So this one is 3 plus x. And this one is, right, yeah. This one is one without a constant term. Okay, yeah, this one is different. So our very top box then would have z, and the exponent, I guess. How do we figure out the exponent on the top box?
The top box, the representative?
The root.
So that would be,
X,
whatever you picked out, like x to the 1 or x to the 2.
Arthur, X is the variable on the top. And do we need X to the 0th on this? Is there any term in there that has that does not involve X? No. So the exponent would be 1. Because it's X times this because the X can be factored out.
I didn't follow any of that. So far, I've got these boxes.
You have an X0?
We have a Z0.
Oh, Z. Okay, if you start with Z, yeah, sure.
Which we should.
Right, we're supposed to. It's backwards. Okay, you're right. You're exactly right.
And then its children are going to have 0, 1, and 3. But I've forgotten why there's a 0 up here. That's what I asked about. How do we find out the exponent of the root? Is it just always 0?
Oh, you might be right.
Yeah. He says on page 357 that the root has exponent 0 always.
Okay. So then our polynomial under the 0 is going to involve y, and this one's going to involve y, and this one's going to involve x. So now I'm confident of that, and this is way smaller. Y, and x.
I've got you zoomed, Arthur, so...
Oh boy.
You've got the spotlight.
So this y polynomial, that thing there is really y to the 0 times x squared plus y to the first times x, and really there's a minus sign in there. So that means one, and examples up. Like that. These are up arrows.
If anyone else is diagramming, if you could also show us what you've done, and I'll zoom in on it. And I see a great whiteboard behind Paul, so I think I'm going to look for one. Maybe we can make use of it.
Filling in some arrows. So here we're saying this polynomial here is a polynomial in y that's like y to the 0 times negative x squared plus y to the first times x. That's what that polynomial is. So in this first term here, we said z to the 0 times, and now I'm working out that polynomial. So that's y to the 0 times, and then some polynomial x, and then y to the first, and some polynomial of x. And we're getting down to the first constant here. Y to 0, so and then x squared. So we would have the 0 is like nothing, and x to the 2, and then we have a constant factor there of -1.
So why does the root node, the z node here, have exponent 0?
That's what I said.
Why doesn't it have exponent 3?
But what about
Z
3?
cubed. It's z cubed.
Well, the root node, are you talking about the diagram in the book?
I'm looking at Zartaj's polynomial in the chat. I don't know if that's the same. Oh yeah. So the z is the 0.
So it's not so.
The exponents. So the top node represents a function of z. The exponents on z are in the second row. So the first row, the exponent on the first row is really meaningless, and it's set to 0.
Yeah, one of the tricky things about this representation, particularly when it's written out in the way that Knuth did, is that you've got nodes in here. You've got little boxes in figure 28D that have like y with a 1 above it, and x with a 3 above it. And I really want those to be, y to the first, x to the third, but that's not what it means at all.
Right.
Yeah, it means y times the variable above it to the third.
But not even y. It means function of y times.
Exactly.
Function of y and maybe some other things times z to the first, and function of x and maybe some other things times z to the first.
You're right. It's not even it's not even y times. It's some function of y, because it could be a constant underneath it that doesn't even involve y.
So anyway, I'm going to try to finish the first subtree of this thing, but I don't even think I'm going to try to write out the whole thing.
But I think the element that you get when you go down all the way is going to be the term for x squared, because on the first level you're going to have a 0 for the z, because there's pieces that don't depend on z, and on the second level you're going to have a 0 for the y, because there's pieces that don't depend on either z or y, and then you have the x, and the exponent on the x is going to, the exponent on the x is, you have an x, y, z, no wait, I lost my picture of it.
So I claim that I have now finished everything below this y. I haven't tried to do this and this yet. I know.
Okay, I think that should be good enough to add at least 1 or 2 terms, but let us, give me a second, Srivatsa.
Arthur, you have an x0, and then on the second level you have a 0, because there's pieces that don't depend on z, and that is a y, so it's y and 0, right? On that second level?
Here?
Yeah.
Yeah, that's y and 0.
And then below it you have an x. Boy.
So below it, yeah, so we have 2 terms. So the part below it is trying to encode this. Y to the 0 times negative x squared, and y to the first times x. So we have 2 children at that level. Y to the 0 times, and the polynomial of x, and y to the first, and a polynomial of x. And this polynomial of x, and neither of these have a constant term. So the constant term here is 0, 0, 0, and then we have the x squared, negative x squared bit, negative 1 times x squared. And then here we have 0, 0, no constant term, and then 1 times x to the first.
I wish you could make that full screen because I can't see it.
You can pin Arthur style and it'll be bigger. So I had zoomed in on Arthur for a while there. Srivatsa, do you also have a diagram?
I can see it now.
I'm gonna zoom in on you
Yeah,
for the recording.
I have a diagram. I'm just trying to. I did not draw all the boxes, but I have some of them.
Go ahead.
1 second. Sorry, this technology.
No problem.
I don't know if this. I mean, it's kind of symbolic. I mean, I did not draw all the.
You can pull it back a little bit. Yeah, that's fine. And
I think this is the tree, but likely I've gotten something wrong. But
it's still really blurry for me.
Yeah, it is actually no.
Yeah, I think the problem is it's not real paper. So it's okay. Maybe I can take a photo.
No, I think what the problem is that your camera resolution is a little low.
Oh, this is worse.
Yeah, light would help, but you know, Srivatsa, the Google Meet settings. If you go into the settings, there's a video setting for the resolution that you're transmitting and receiving. So I wonder if you've got it to the highest resolution possible.
Not sure. Let's see if it's any better. Is it? I can also try. Yeah, it's probably not worth it at this point, but no.
Maybe it is just the lighting.
It is not there, but forget it. It's okay. I'll just take a photo and upload link in the chat or something.
Okay.
And all I know, this is probably wrong. So
so that's great. We're a little over, past 3 p.m. here in New York. So we'll take a 10-minute break. When we come back, we'll continue our discussion and try to work out some of the steps using the diagrams we've seen. So please feel free to turn off your cameras, mics, and refill your coffee or tea. The recording will continue and the meetup will stay up, and we'll see you guys at 3:20 New York time. Okay, we are back. And we were just discussing the algorithm A for adding polynomials, and we seem to have gotten ahead with the diagramming. So if somebody could walk us through a couple of those steps.
Well, so Srivatsa's and mine are basically the same, except that Srivatsa forgot some 0, 0 nodes, which Knuth implies that they, well, in the diagram he shows 0, 0 nodes, and on page 357 he's saying x is a variable, n is greater than 0, 0 is equal to e sub 0, is less than e sub 1, is less than. And so e sub 0 always has to be 0, even when there's no like why do these nodes there? Like I don't know why these nodes are there actually. Right.
I imagine the algorithm may use it somehow. Yeah,
but I wouldn't say how. I can only assume they're indispensable for some reason.
Oh, so they're like a head node? In a circular list, they're like a head node so that you have something, if you find something later on to attach it to, you have a node to attach it to? Really?
Or so you find something, well, in step A4 of the algorithm, I notice he is saying, go to the left, and if you've reached exponent 0, do something special.
Right, like a head node, like you're at a head node.
Yeah, so he is using that exponent 0 to mean something special, or to kick out into a different part of the algorithm.
Right. I think the head node explanation makes sense, because if you're only going circularly, then you probably don't know when you've reached the end if you don't have a special node, I guess.
Well, I mean, the exponents are sorted. It wouldn't be that much harder to just look to your left, and if that guy's bigger than you, you're at the head. But maybe this just easier to express.
He starts at the 0 node, and then he moves to the left, and that first time it's going to be bigger, and then it gets smaller and smaller and smaller until you get back to the 0. It's just the way the algorithm is set up. I think you're right, Arthur. I think you could probably do it without it. Just might make it a little harder to insert a node because you don't have anything to insert it to. So when you're inserting a node on the right end, but there are cases where you have to make a fake node in that one step. I think it's A3. You make a fake node. You make that 0, 0 node so that you have something to insert it to. Yeah, that makes sense. It probably makes the algorithm simpler to have the head node there.
Could we try?
It's 0 times all the variables to the 0th power, which doesn't add anything to the polynomial, but it's there to be a head node.
Right.
Could we try
the
head of a doubly linked list?
Yeah. You don't really need this node. I find it weird because normally Knuth is very down in the.
If he can save a bit, he will in his algorithms.
Yeah, but here we're in his figure 28D. We've got 2 whole nodes that don't really communicate any information. He's just using them to make the algorithm simpler. So yeah.
Could we try adding the z to the 0 terms in both polynomials? If one of you, Srivatsa or Arthur, if you could leave your diagram up, hold it up, I'll zoom in on it, and somebody else can maybe just walk us through 28D and our diagram of the second polynomial. Okay, Arthur's doing it, so I'll pin his diagram, and Yeah, anyone, I mean, Arthur, if you want to do it, go ahead. Srivatsa, Michael, Miguel, Paul.
Not me.
Okay. So we're looking at the z to the 0, adding the z to the 0 terms.
Which means this subtree.
Yeah. Exactly. Z to the 0 is the Z node at the top, but the 0 comes from the second level node.
So I don't even know. You have to be looking at this and figure 28D and the algorithm all simultaneously.
Yeah.
Maybe, what if we had, can we get one person, tell you what we'll do. Let's get one person to read the algorithm. I will be pointer Q on my diagram, and someone else can be pointer P in the figure 28D. And maybe we can walk through it that way.
Okay, that sounds good.
So I'll
so
start
Arthur owns his terms, and he'll move and he'll point to where the reader, the algorithm reader or the step reader, tells him to, and then the third person can explain what's happening with 28D. So who will be the algorithm reader? We're looking at the case where we will have found a matching term.
Well, I suggest, does anyone have the physical book or?
Yeah, I've got the physical book, but I'm lost. So I can read, but I don't understand.
So you should be pointer Q, pointer, you're pointer P. So put your finger on figure 28D at the top of that.
Got it.
And then how about Zartaj? You be the reader and start with A1.
Okay, all right. I'll be the reader. So A1 is saying check down of P if it's null. So P would be Paul.
Okay. So down is the bottom right-hand thing.
Correct.
Well, down is the downward link from the top node, and it's not null. It's just pointing to the second level.
Right. So down.
I see the down. There are fields, and the down field is the bottom right.
Yes.
Exactly.
Is that right?
Yes.
And then that's pointing to.
Look at the node on the top that says Z and 0. Okay. The down. Oh, right. The down node is the bottom right corner, and it points down to a node that says X and 0. So it's not null.
It's not null.
Yeah.
Okay.
Right.
So I think what I'll do is I'll ask a question, and you look at your diagram and you provide the answer, or and then I'll tell you what should happen. So down of P is not null. So we skip that piece. So then we say if down of P is not null, then if down of Q is null. So is down of Q null?
No.
Or if, okay, so now we want to compare CV of Q, that would be Arthur. What is CV of Q?
Is Z, letter Z.
If it's less than CV of P.
So CV of P is Z, because I'm in the UK. So are Z and Z the same?
I think that is less than Z, so they're equal.
So, they're equal.
They're equal. So then we go to, otherwise, if CV of Q equals CV of P, set P, that's Paul, to down of P. So you're going to follow the down link of P, and then that will become the new P. So do you know where we are now?
So I'm now sat at this one. Yeah, so at 0x. So that's, I am, yeah.
Okay, and same thing with Q. We set Q to down of Q.
All right, so I'm now pointing at 0y.
Okay, and then we repeat this step, meaning that we're going to do the same thing that we just did. We're going to check CV of Q and CV of P. If they're equal, then we essentially are following the down links while the two CVs are equal. So where will we end up?
Well, I'm actually at this step. Just keep going. Just keep going with A1.
Yeah.
So
if CV of Q is less than CV of P.
Right,
So
CV
right
of Q is less than, so what is CV of Q?
It's Y.
What is CV of P?
X.
All right.
Is Y less than X?
No.
Okay, so Y is greater than X, so set Q to down Q. So only Q is following the downlink.
Okay.
Okay.
And then repeat this step.
All right. So we start over with A1. Is down of P null?
So down of P is not null.
All right. Is down of Q null? No.
And then compare CV of Q and CV of P.
So CV of Q is X.
So CV P is X, so they're equal.
So set P to down of P and Q to down of Q.
Okay. So I'm at 0, 3.
And I'm at 0, 0. And we repeat the step again.
Okay, so down of P is null?
It's null. Yep.
Down of Q is null?
Also, yep.
Okay, so now we go to A2.
A3.
Okay.
Sorry. Yeah, we go to A3. So A3 is match found, which makes sense. Okay, so at this point, P and Q point to corresponding terms of the given polynomial. So addition is ready to proceed. Set CV of Q to CV of Q plus P. Remember that Q will be the result polynomial.
Okay. So what is CV of P?
CV of P is 3.
All right. So that means I go in here and we're going to change this to change the CV, not the exponent. Let me call it 3. All right.
So what is the new CV of Q? It's 3.
Yes.
So then, continuing with step A3, it says if the sum is 0,
it is not.
And if exponent of Q is non-zero, then go to step 8. So we'll ignore that. And then there's a further check for the exponent of Q being 0, which it is actually. So what is exponent of Q?
0.
0. So that means we actually go to A7. A7 is labeled move Q up to right level.
Right level.
It's already weird. I'm like, what about my right child? What am I doing with that? All right, here we go. Move Q up.
Yeah, what happened with that?
We'll find out. If up P is null, go to A11.
So what is up P, Paul?
Up P is...
Is it null or not?
It's not null, right?
No.
Because we got there by going down.
Okay, so it's not null.
But
so
P has been mutated, hasn't it? Sorry, I'm confused. So P has been mutated, right? So
no, P has not mutated.
Okay.
P the pointer. I mean, you're tracing around in the structure.
Yeah.
You've gone down several times.
So is P the pointer?
Oh yeah, P.
Yeah,
Sorry,
P is still the whole
pointer,
thing,
right? Yeah, so we need to distinguish between the node and the pointer.
Right.
The nodes that P will point to will not change, but yeah, P itself is changing.
And
So,
like sometimes Knuth refers to the whole polynomial, like the first polynomial, as polynomial sub P. Like in step A6, he says a row of polynomial P has now been completely traversed. But I think there he means the left-hand polynomial.
Right, got it.
Right? But P itself is a pointer that's tracing all around in the structure.
Yep.
Okay, so in step A7, Q will be assigned up of Q 0 or more times until CV of up of Q is the same as CV of up of P. So we're sticking with where P is. We know what up of P is. It's not null. We're just going to keep moving Q upwards until it matches the up of P.
So up of CV of up of P is X.
Okay, and CV of up of Q is also X. So done.
Okay, so Arthur, do you want to move your finger up one level?
No, I want to move it up 0 or more times.
0 or more times. Yes, that's right. Okay, so return to step A4. A4 is advance to left.
Oh, good.
After successfully adding a term, we look for the next term to add. There we go. Set P to left of P. So that's Paul.
So P is left of P. So
what is it?
Oh, so it wraps round to the right.
Yes.
So its value is 1, exponent is 2.
Okay, so then there's a check on the exponent of P. If it is 0, then go to A6, which is it's not. Otherwise, set Q to left of Q 1 or more times until the exponent of Q is at most exponent of P, which means less than or equal to exponent of P.
Right. Okay, so 1 or more times. I'll do it once. And what was exponent of P?
2.
This is also 2.
Okay, so that's your condition. It's true. If then the exponent of Q equals exponent of P, return to step A1. So I believe that's the case here.
That is the case.
Okay, so we go back to step 1, which was essentially trying to go downwards and try to find a matching term.
Right.
So
Right, but we're already at the bottom, so.
We're already at the bottom. So what will happen then? What will happen is I think we'll go to step A2.
No. Follow the algorithm.
That's true. That's true. If down of P is null, then set Q to down of Q 0 more times until down of Q is null and go to A3.
All right.
So down is null, I believe.
And down of Q is
already there.
null.
So
nothing
A3 is match found, which we had done before, and addition is ready to proceed. So set CV of Q to the sum of CV of Q and CV of P.
So what is CV of P?
1.
1, and I add +1 and -1, and I get 0. Oh, fun stuff is going to happen.
Oh, okay.
All right, so I have just done that step, and now
if this sum is 0, and if exponent of Q is non-zero, go to step A8. Is exponent of Q non-zero?
Yes, it is.
Okay, so we go to A8, which is titled delete the 0 term. So now we've got a new pointer R, and that is assigned Q.
Well, I guess
okay, you got another finger. Actually, you have 2 hands.
Q then is assigned right of R. So what was R?
Well, R is Q.
They're both. At this point, they're both the same.
They're both the same, right? So Q then becomes right of whatever it was before.
Okay.
And same thing with a new pointer variable S. So S gets left of R.
All you're doing is deleting that node and putting it on the free list.
Q is right of R, S is left of R. Okay, so Q and F are the same.
You need both those pointers.
S, right of S is Q, and avails R. Right, yeah. So here's what we're doing. We're getting rid of this node.
And adjusting the 2 links for the
left and the right.
And they're now that node is going to be a single node, solitary node pointing to itself.
Circularly linked to itself.
It's going to be a circular link to itself. That's why you need both. If you could have been in the middle of a long list, in which case S and R would have been different nodes,
Okay.
and you would have had to join them together.
Okay, but now we need to evaluate this condition. If now the exponent of left of P is 0 and Q equals S.
Q does equal S.
And the exponent of left of P is 0, indeed.
It is 0. Okay, so go to A9. A9 is delete constant polynomial.
Which is
Cancellation, the explanation is cancellation has caused a polynomial to reduce to a constant. So a row of polynomial of Q is deleted, meaning the whole thing, one
The whole
row
thing
will be
goes
deleted.
the whole thing goes away. So
So,
you got another thing to delete.
so can we just figure this out? Do I really need to go through each of the, because there's a lot of assignments here.
I think it's worth. Well, actually, I kind of want to pause at this point and say, what is exactly the state of this polynomial at this point? Why am I pointing to the number 3 and yet we're going to delete it? It made sense that we were getting rid of a 0, but isn't this a 3? I just wrote down this 3. We're going to get rid of it? I wanted it. So what is going on here exactly? We're going to take this. We're going to take this CV, and I see we're assigning CVQ gets CVR at one point. So I guess we're
think
going to move up eventually.
I think the point is that when it becomes constant, then you no longer need the head node, the root.
Okay. So in other words, we're basically going to take this 3 and move it up here.
Yeah.
And get rid of the X. Well, let's see if that happens.
Okay, so let's go through the motions. So we assign Q to R.
Okay.
Then we assign up of Q to Q.
Okay.
We assign down of R to down of Q.
Okay. I mean, that's basically unlinking this node.
Yeah, so this will be all Q. There's no P involved here.
And Q down R. And then CV of Q, which is now the X0 node.
Mm-hmm.
CV now gets CV of R, which is 3.
Yeah, so we're moving it up. And then we free the R node.
Okay.
And then
S to down of Q, but in fact that's null. So most of the magic doesn't happen at that point. With this.
Okay, is this the net result of A9 that you're pointing to?
Yes. And at this point, Q is where my finger is, and S is null.
S is null. Okay, so if S is null, then I think we go to A10.
Yep, that sounds good.
Yeah, so A10 is titled 0 detected, question mark. If down of Q is lambda, so is down of Q lambda or null?
Yes.
And is CV of Q 0?
No.
No.
Because it's 3.
Oh, okay. So 0 is not detected. So then what we do is we go to A6. A6 is titled return upward. And the explanation is a row of polynomial P has now been completely traversed. Set P to up of P. So Paul, that's you.
Yep. P of upper P, so I go to P is now pointing to 0x.
Okay, so you moved P up, and now we go to step A7, which is titled move Q up to right level. Paul, is up of P null?
Up of P is not null.
Okay, it's not null. So we go to otherwise set Q to up of Q 0 more times until the CV of up of Q is the same as the CV of up of P.
And the
Right, so CV of up of P is Z.
And the CV of up of Q is Y.
So move it up.
So we'll move it up, and now the CV of up of Q is Z.
Okay, so now we satisfy the condition, and it says return to step A4, which is titled advance to left. So we've successfully added a term. We look for the next term to add.
Okay.
So set P to left of P.
So P of left is left of P. So P now goes to the X3. Yeah, wraps all the way around.
Okay, and
So
then
X3.
is exponent of P 0?
No, it's 3.
Okay, otherwise set Q to left of Q one or more times until the exponent of Q is at most the exponent of P.
So at the moment, exponent of Q is 3. What is exponent of P?
3.
Okay.
So condition is true. If then the two exponents are equal, which they are, return to step A1. Okay, so I think that's pretty good. Do we want to do some more, or do we get a sense of what's happening?
Arthur wants to go.
So what state is Q in now? So what have we added? Have we added anything yet?
I'm willing to keep going, but also not really willing to go past 4, which means I don't even think we're going to finish.
Okay, so since we don't have any hope of doing the rest of the material, I think we should keep going and just just do the algorithm. So we're back on step A1, and you remember what the deal was there, right? So we want to go downward till we find two matching terms of the polynomials, or else we determine that the insertion of a new variable must be made.
Oh.
So is down of P null?
Down of P is not null.
All right. Is down of Q null? No. What is CV of P?
CV of P is X.
CV of Q is also X. So they're equal. So set P to down of P.
P to down of P, okay.
Q to down of Q. And repeat this step.
Yep.
Is down of P null?
Yes.
All right. So we go until down of Q is null, which it is, and we go to A3. At this point, P and Q point to corresponding terms, so addition is ready to proceed. Set CV of Q to CV of Q plus CV of P. What is CV of P?
1.
And we have -1. Oh boy.
Oh.
0.
Okay, so then we go to, then we actually need to check, is the exponent of Q non-zero?
The exponent of Q is 0.
Okay, so if it is 0, then we go to A7, which is move Q up to right level. And then we check, is up of P null?
Up of P is not null.
So it's not, so we move Q up. So we set Q to up of Q 0 more times until the CVs match.
Right, so what is CV of up of P at the moment?
CV of up of P is X.
And CV of up of Q is also X.
Okay, so then we return to step A4, which is advance to left. After successfully adding a term, we look for the next term to add. Why did we not need to delete the 0 term this time?
Because it's still got stuff to its right.
Okay.
That we haven't gotten rid of yet.
Okay, so set P to left of P.
Okay, so P goes to 1 minus 3.
And is exponent of P 0?
Exponent of P is 1, so not 0.
So we set Q to left of Q 1 or more times until the exponent of Q is at most exponent of P.
Okay, what is exponent of P at the moment? Is 1?
1, yep.
So exponent of Q, having moved left once, I get 3, or sorry, no, I got 1. Exponent of Q is 1.
Okay, so then if they're equal, which they are, we return to step A1, which is the downward move. And yeah, so I'll let you guys do that.
Is down of P null?
Yes.
All right, then I move down Q down until its down is also null, which is not no up there. Go to A3, match found. Set CV of Q to CV of Q plus CV of P. What is CV of P?
CV of P is -3.
-3. Oh, look at that. We have another 0. So CV of Q is now set to 0. If this sum is 0 and x of Q is non-zero, that is true, it's 1, go to step A8. Step A8, delete 0 term. Set R to Q, Q to right of R, S to left of R, left of Q. Oh, geez. So this is Q. R is this is Q now. R is the other one. This is Q and S. We link Q to itself, and we get rid of R. Q is S. What is exponent of left of P?
Exponent of left of P is 0.
Okay, if now exponent of left of P is 0 and Q equals S, which is true, go to A9. A9, delete constant polynomial. Here we are again.
Yeah, now you're going to delete it, the one that you wanted to delete before. Because
yes, exactly.
Because you couldn't delete it when you wanted to delete it originally because there was that term expressed on the right. But now that term that was expressed on the right has been deleted, you can now delete this one.
And this time when we bring the CV up, when we do that, CV of Q gets CV of R in step A9, we're overwriting X with 0. And when Dale gets R, that goes back. Set S to down of Q. If S is non-null, it is null. All right, so I think that now Q is here.
Yeah.
Let's begin step A10.
Yep.
So A10 says if down of Q is null, which it is, CV of Q is 0, which it is, and exponent of Q is non-zero, which it is, set P to up of P.
Okay, P to up of P. So, yeah, P and goes to this 3x.
So A8, delete 0 term. So let's set R to Q, Q to R, S left of R, left of Q to S, right of S to Q, and available R.
Deleted that one too.
At this point, Q is going to wind up being over here. So at this point, I think, I may have lost the thread of things, but I think Q is now back at the 0y node.
Okay.
And this time when we did that, like, S left of, what did we do? I hope Sartaj is still paying attention, so I'm starting to lose the thread of, we just did, shoot.
I do have you zoomed in, Arthur. I was trying to figure out the result.
You're running ahead, that's the problem. I have immediately forgotten what I just did. Did I just do step A8?
Oh, yeah, I'm not sure.
I think that I did. So that time in step A8, when we did S gets left of R and left of Q gets S and right of S gets Q, we were actually linking up not just a node with itself, but linking up these two nodes so that they remain in a circularly linked list.
Oh, okay.
That was a non-trivial application of step A8. So if now X of left of P is 0, What is exp of left of p?
0.
It is 0. Okay,
Yep.
and q is s, but in this case, q is not s, because there are 2 children in this node, in this row. So we will not go to A9, we will instead go to A4. So A4, advance to left, look for the next term to add. Set p to left of p. Oh,
I may have made a mistake.
no!
No, sorry. Can we? Oh dear. Can we wind the stack back one? So I'm at 3x now. And did you ask me if the exponent of left of p is 0?
I did.
Oh, it's not. It's 1.
Wait, that's okay. That's okay because q wasn't s anyway.
Okay. So now what do you want me to do? So p is left of p, I think.
Yes, p gets
Okay.
left.
So yeah. Okay.
So that node that you just looked at and you told me it's exponent, now you're pointing p at that node.
Yes.
All right. And what is exp of p?
X with p is 1.
All right, so it is not 0, so we don't go to A6. Otherwise, set q gets left of q 1 or more times until exp of q is at most exp of p. So q goes left at least once. What is exp of p?
X with p is 1.
Exp of q is also 1.
1. Yeah.
So, okay, so we're done with that step. If then exp of q equals exp of p, which it does, return to step A1. This is starting to look familiar. And I think this is the last time we're going to do this step. Okay, we're almost done. Except that we have to descend this one.
Promises.
So now we're adding this polynomial to whatever p is now pointing at. Is down of p null?
No.
It is not. So is down of q null? No. What is CV of p?
CV of p is y.
And CV of q is also y, so they are equal. So set p to down of p.
Okay. P goes to p. Okay.
Q gets down of q, and repeat the step. Is down of p null?
Yes.
Down of q is also null. And go to A3, match found. At this point, p and q point to corresponding terms. What is CV of p?
CV of p is 0.
Okay, so CV of q gets the sum of 0 and 0, which is 0. So the sum is 0, but exp of q is not non-zero. So we don't go to step A8. Instead, what is exp of q? It is 0. Yes, go to A7. Move q up to right level. If up of p is null, is up of p null? No.
No.
Otherwise, set q to up of q 0 or more times until CV of up of q is CV of up of p. CV of up of q is y. CV of up of q is also y. So we just leave that alone. Return to step A4. Advance to left. After successfully adding a term, look for the next term to add. P gets left of P.
Okay, P goes to left of P.
And then, what is exp of P?
Exp of P is now 1.
All right, so it's not 0. So otherwise, set Q left of Q 1 or more times until exp of Q is less than or equal to exp of P. So what was exp of P? It was 1?
It's 1, yep.
All right, so we go over here, and now exp of Q is also 1. So they are equal, so we go back to step A1. We're going to add these polynomials. What is down of P?
Down of P is not null.
Not null. All right.
Yep.
Down of Q is also not null. What is CV of P?
CV of P is X.
Oh, yeah. Right. X. Mine is also X. Therefore, set P to down of P, Q to down of Q, and repeat this step.
Okay. P to down of P.
So down of P is now null?
Null. Yep.
It is. All right. Down of Q is also null. Go to A3. Match found. What is CV of P?
CV of P is 0.
and CV of Q is whatever it is. We're adding zero to it.
Yeah.
Not zero. And if X of Q is non-zero, well, that's not true. So we don't go to step A8. If X of Q is zero, which it is, go to A7. A7, move Q up to right level. If up of P is null, which it is not.
Which is not. Yep.
Otherwise, set Q equals up of Q 0 more times until CV of up of Q is CV of up of P. What is CV of up of P?
X.
CV of up of Q is also X. Return to step A4. Set P to left of P.
P to left of P. Okay. Yeah.
Is X of P 0?
No. X with P is 1.
All right. So Q gets left of Q one or more times. Wait a minute. I feel like I might have messed this up at some point. Maybe not. Let's keep going. But I feel like
me. It could easily be me.
oh, now we're moving.
I've had the easy job here, so
Q only
it
has
has been much more complicated.
one or more times until X of Q is less than or equal to X of P, but it's 0. So I guess I stop here. If then X of Q is equal to X of P, what is X of P?
X with P is 1.
Okay. So X of Q is 0, which is not 1. So we don't return to step A1, and instead we do step A5. Oh boy. So here we go. Step A5. It's a new step. We found a new step.
Yeah, because you got to insert this one. This is the first one we're going to insert.
Yeah.
I think you actually
never going to
followed
happen.
it correctly.
All right. So R gets a new node out of avail. That's what that notation with the double arrow means. Set up of R to up of Q, down of R to null, CV of R to 0, left of R to Q, right of R to right of Q. So we're inserting to the right.
Yeah, you're inserting. You're going to insert a node that matches the P, so that you can add the two coefficients together. So you're inserting it with a 0 because then you're going to add 0 to whatever P is pointing to. And it's matching. You're matching whatever exponent he's pointing to.
Yeah. So this is my R and then adding. So this is Q and here's R and CV of R gets 0 and X of R gets X of P. What is X of P?
X with P is
1.
1. All right. And then finally set Q to R. So now Q is here, and we go back to step A1. It says we needed to insert this new term in the current row in order to match a corresponding exponent polynomial P. Now we go back to A1, and we try to add this polynomial one that we just found in P. So is down of P null?
yes.
So down of Q is also null. Go to step A3, match found. CV of P is
CVP is 1.
1. So I add that to 0 and I get 1.
Okay.
If the sum is 0, it is not. So if X of Q is 0, it is not. Advance to left. Set P to the left of P.
Okay, P to the left of P.
If the exponent of P is 0, is the exponent?
Which it is.
It
Yes.
is. Go to A6. Return upward. Hooray! Another row of polynomial P has been completely traversed. Set P to up of P.
I think we're done.
I don't know about that. Is up of P null?
No.
So set Q to up of Q 0 more times until CV of up of Q is CV of up of P. What is CV of up of P?
CV of P is X.
And CV of up of Q is also X. Return to step A4. I've still got I haven't moved my finger in a while. Set P to left of P.
P. Okay.
Is X of P 0?
No. I should have gone up a level at this point. No, because I've gone back to where I'm still in the same list.
Well, when I said return upward, a row of polynomial p has now been completely traversed, set p to up of p.
Okay. So no, I think I lost sound at that point. My phone was doing something. So.
Phew. We almost went in an infinite loop there. All right.
Yes. Okay. So, let's go back to there.
Okay. So return upward, a row of polynomial p has now been completely traversed, set p to up of p.
Yep.
Okay. So now that has been done. Now I'll ask again: is up of p null?
No.
Okay. What is CV of up of p?
CV of up of p is y.
It's y. And in my case, it's x. So I'm going to go q gets up of q. And now CV of up of q is also y. Which is CV of up of q. They are equal, so return to step A4. Set p to left of p.
E to left of p, okay.
What is the exponent of p?
0.
It is 0, so we go to A6 and return upward. A row of polynomial p is now completely traversed. So again, set p to up of p.
Right, I can hear you again now.
Okay.
Sorry, my phone is.
Step A7, is up of p equal to null?
No.
Still no. All right. What is CV of up of p?
CV of up of p is y. Have we gone up a level again? Sorry, am I?
You missed it. We got up.
Missed it. Okay, we're going up. Every time we go up a level, my sound cuts out. So
right after I said set p the up of p, you said, "Okay, this time I got it."
Did I?
Yes, it was very.
Oh, okay.
Yeah,
no,
sure.
no, I think I couldn't hear you there.
Okay. So set p to up of p, is up of p null?
No, it's the root.
Okay. So what is CV of up of p?
CV of up of p is z.
Yeah. Okay. So I'm going to go up until CV of up of q is z. So now it is, and return to step A4. Set p to left of p.
Okay, p to left of p.
What is x of p?
X of p is 0.
So we go to A6 and return upward. Hooray! Set p to up of p.
P to up of p, yeah, I've definitely got it.
All right. So now is up of p null?
Up of p is null.
Go to A11. Terminate. Set q to up of q 0 more times until up of q. So we bring q back up to the root of the tree.
That's
and now
what I meant by we're done. We just went up and up and up and checked for more until we were done. And I don't know whether you noticed or not, but Arthur, hold your thing up again. On the second, on the third row, the second and those two children, we never touched those. But we didn't need to, because they represent terms that aren't in the polynomial that we were adding.
Right.
So if we're adding a small polynomial to a large polynomial, we could skip a lot of notes. In this case, we only skipped those 3.
Yeah,
okay.
I agree with that.
So I think that's why you thought maybe we weren't done yet, because we hadn't seen those 3 notes.
But we knew it didn't have to.
But to me, I could tell that we were done. It's kind of weird the way that we do the leftmost tree first, and then we advance things to the left, which goes to the rightmost end, and then work in. That's just weird, but it works.
Yeah.
And so now I'm going to try to convert this back into a polynomial, right? So it's z to the 0 times, and then a polynomial y, which is y to the 0 times 3, so that's just 3, plus, and then y to the first times x, which is xy, and then we have z to the first multiplied by y to the first x to the first minus 1 other thing was removed. So I think, so I got that, which then boils down into 3 plus xy minus yz plus xyz.
Yeah, I think that comes. Oh, is this right? I think there is something has gone wrong.
That is quite possible.
Yeah.
Yeah, when I did the straight addition, all the z terms disappeared.
Yeah, that xyz should have gone away.
So it seems to have carried or added an extra x somehow in that last term.
Oh, here, let me write down in the chat the polynomials that we.
It was Paul's disconnect. It was. I blame Paul.
Yeah.
It's the audio.
Janky
It's the
cable
audio.
over the Atlantic. Yeah, we have an unreliable node in our distributed system.
Yeah.
Cosmic Ray flipped a bit.
Yeah, what is the Byzantine version of this addition of polynomials?
Yeah. Anyway, I need to go now, unfortunately, but thanks very much for organizing this.
Well, thanks for being a good sport. So this was unusual, our tag teaming here, but I had a lot of fun.
No, I
great.
actually learned a lot, so thank you very much.
I mean, sooner or later, you have to do this stuff. Like, you can either do it alone, or you can do it.
No, it's much more
with
fun in a group. So, do you run this every week? Is that the schedule?
every Saturday, same time. So I think you guys are 5 hours ahead, right, these days?
Yeah, so it's just gone 9 p.m. here. So.
Okay. Yeah. And Srivatsa, it must still be morning for you, or is it now?
Yeah, so
it's 1.
It's 1. So okay, cool.
So you're sat in the middle of the.
Right.
New York's right in the middle of the two. So. Anyway, thank you very much.
Great. Yeah.
I'll see you.
Thank you, folks. So next week we will continue with the topic that we weren't able to finish today, and then I'll add some more stuff. So thanks a lot. Bye-bye.
See ya.